Yesterday, Tesla published a white paper about, of all things, numbers. Boring, you might think, and pointless, but Elon Musk tweeted, "This is more important than it may seem at first." And you know what? It's actually fundamentally important to how Tesla's deep neural network training is done, how they store billions of miles of data, and it will be a critical part of making Dojo the fastest neural network training computer in the world. Let's take a look. For those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. So I'm gonna geek out about numbers today, but first there's just so much happening in the Tesla world that I wanted to mention two things that just popped up in the news this morning. One of them really, really good, and the other one is just part of the entire Missy Cummings deal. The first bit of news, and I'll link this in the description, is that Hertz has decided to team with Uber and Carvana in a big shift to electric cars. So very briefly, as I mentioned in my last video up here, Hertz has ordered 100,000 electric vehicles from Tesla, which is amazing, but this new article then goes on to say that they're also making a deal with Uber and also with Carvana to allow Uber drivers to rent Teslas through Hertz, pay a lower rate, and have all of the things like insurance and all of that kind of stuff and upkeep and everything taken care of by Hertz. So that's really cool. And then Carvana on the far end means that Hertz can sell the Teslas directly to Carvana when they reach end of life, and Carvana can then take care of selling it, which means a completely smooth path from buying the cars to utilizing them very, very heavily while Hertz owns them both for rentals and then selling them to eventual consumers through Carvana. So that's all wonderful. The part that's kind of is a continuation of the Missy Cummings saga, and I've done a video on this as well. But Pete Buttigieg, who's the US Transportation Secretary, has weighed in on the whole Tesla Missy Cummings saga on Missy Cummings' behalf and kind of called Tesla to the carpet about their full self-driving. They both invited Elon Musk to come talk to them, but this certainly seems like a really bad news that essentially, you know, again, we've talked about how the Biden administration has seemed hell-bent on really putting up roadblocks in front of Tesla. And I really hope that eventually Pete Buttigieg, at least, if not Missy Cummings, realizes that the actual competition is not anybody in the United States, it's actually Chinese companies. And if they stop Tesla from doing what they're doing, all they're doing is opening the door to a Chinese company solving full self-driving first. And if they do that, then China has full self-driving and nobody else does, and that means that they get to export that to the world. So you guys better pay attention. You're not actually having a Tesla versus Ford versus GM kind of thing. You're doing a Tesla versus China thing, and you need to put the United States first. And if you put up roadblocks in front of Tesla unnecessarily, obviously safety is important, but the data clearly shows that Teslas on autopilot are safer than human beings right now, and that's only going to get more so. So I think that, you know, the small-mindedness of the people in office right now is kind of outrageous. Anyway, I don't want to focus on that today. I want to talk about numbers. So let's talk about numbers. So you probably think to yourself, okay, a number is a number. What the hell? But numbers are not numbers when they're stored in computers. So we have to back up a few steps and kind of set the scene for all of this before I can really explain what's going on with Tesla's white paper that they released yesterday, which is also linked in the description. So first of all, what is Tesla doing? Well, they're doing what Elon Musk always says. They're doing first principles thinking, all the way down to what it means to actually be a number. So you think to yourself, there's a number, so I'm gonna use an example number today that I'm just completely drawing randomly out of my brain, which is 42069 or 42,069. So that's my example number for the day. This is base 10, by the way. I'm going to use base 10 throughout a lot of these examples just to make it easier for you to understand this. Everything that they're talking about in the white paper is binary. So that's base 2, right? Zeros and ones. But that's a little more complicated and it adds another layer of complexity to what I'm going to talk about. So most of my examples are going to be talked about in base 10 numbers, just to make it clear. But I want to be very, very clear. I'm going to give you the flavor of what's going on with this white paper, but not the actual details. If you're really interested in it, you definitely need to read the white paper. It's very clear. It explains exactly what's going on. It's super, super cool. And it's, you know, I'm totally geeking out about it. But anyway, what's the difference between the number 42,069 and the number 42,069 that's stored in a computer? Well, the main thing is that in the real world, it's part of a continuity of integer numbers from, from negative infinity to positive infinity. In other words, it's an infinite range of numbers. It's one of those numbers. Computers can't do infinity, right? They have a limited amount of storage and a limited amount of precision in their numbers. And so they always have to kind of chunk it, I guess, or you could say estimate, but essentially what they have is they have two values. They have precision and they have range. The precision is how many numbers you can represent for any given number, and the range is how big or how small of a number you can get. And those two aspects of a number that's stored in a computer are really, really important to our discussion today. So let's discuss those in more detail. So again, precision is the number of digits that you can store. So, right, so 4206931415926, whatever. You just keep, saying numbers. Eventually in a computer, no matter how big the bit depth becomes, you're going to run out of space to represent a number like that. So that's precision. Precision is not infinite. You have to make a choice about that. So you might think to yourself, well, let's just use really, really big representations like 64-bit floats or 128-bit floats or 256-bit floats, right? You can use those, absolutely you can, but there's a huge consequence to that. And the huge consequence to some extent is processing, but even more so is memory and bandwidth. So memory, of course, is how much room it takes to store something, right? So an 8-bit number takes half the room of a 16-bit number, and 16-bit number takes half the room of a 32-bit number, et cetera, et cetera. So that's one thing. Then there's the bandwidth, which is passing that data back and forth to various things, to memory, to processing units, et cetera. So as you do that, you're having to pass more information around, and that bandwidth becomes very, very taxing as you start doing this more and more. So just as a quick recap for those who don't really know, an 8-bit number can represent 0 to 255, so that's 2 to the 8th power, or 256, and then you knock it down by 1, right? So 0 to 255. Or in the case of the IEEE standard, it's actually 1 to 254 because you've got reserved bits for nan and for infinity, which is not a number, which is dividing by 0 essentially, and infinity, which is an unrepresentable number. So anyway, that's an 8-bit number. Then with a 16-bit number, which is 65,536, you get 0 to 65,535 because again, you're shifting it down 1. Or again, if you take account of the not a number and infinity, it's actually 1 to 65,534. If you get a 32-bit number, it's about 4.2 billion. And if you get a 64-bit number, it's about 18.4 times 10 to the 19th. So all of these are common, and you can see how the more bits you get, right? So that's just the longer this word is, this computer word is, the more numbers you can represent there and the more precision you can get, right? With a 64-bit number, you get 18, I don't even know, times 10 to the 19th. So 19 zeros. So that's a lot, and that's base 10, so it's even more than that in binary. And of course, then you can use 128-bit numbers and larger. So you can often use that, but it takes much, much more bandwidth to process this and to store it in memory, and it slows things down. It takes up a huge amount of memory. And if you think about that, right, if you go from 8 to 16 bits, that's 2 times per dimension per doubling of size. And when you get to things like matrix math, it actually gets even worse because it's, if you double the bit depth, you actually are increasing it 2x per dimension. So if it's a square matrix you're multiplying, it's actually 2x times 2x, which is 4x. So it's going up by 4 times instead of by 2 if you go from 16-bit to 32-bit representation. So the deal is if you don't need the precision, you can reduce the size of these numbers because you don't need all of those extra digits as you go. So you can actually reduce the size of these numbers to a large extent, and you can save a lot of memory and a lot of bandwidth. Which now takes us to range. So what is range? Range is the size of the number, and you may say, well, wait a second, that's exactly the same thing as precision, but it's not, because the common storage format for computers is what's called floating point. And what that is a mantissa and then an exponential number, right? So in base 10, that might be something like, again, 4.2069 times 10 to the 4th or whatever, right? So that's 42,069 because it's 4 zeros. So basically you're taking a number 4.2069 and you're multiplying it by a number with just a 1 followed by 4 zeros. And that gives you 42,069, which is exactly what I started with, right? So that was the thing I began with, but this is a way of representing it so that it's always the same. And the floating point just basically means that the decimal point floats where it needs to go. So the term on the left is called a mantissa and the term on the right is called the exponent. And so now you can see that the precision and range are actually separated because the exponent gives you the range. So the bigger the number you have capable of representing in the exponent, the more range you can get, the bigger or smaller that number can get. And then on the other hand, the number in the mantissa represents the precision. So if you only have 3 digits of precision in the mantissa, so that would be 4.21 because you might round up from that 69, and we're going to get into rounding in a little bit. But anyway, so if you only have 3 digits, that just chunks off that thing, but the range can still be really big because the exponent can be big. So basically you just have to realize that what you're doing is precision and range are separating out the number of digits you're representing and the size of the number. And also realize that the range can get very, very small as well. If you make a negative exponent, it's less than 1. So if it's 10 to the 4th power, it's 1 followed by 4 zeros. But if it's 10 to the negative 4th, it's 0.0001. So it's actually moving it the other direction. So you can make small numbers and big numbers with an exponent, and that's really cool. So just to reiterate, the mantissa represents the precision, the exponent represents the range. Very big positive numbers in the exponent are very big numbers, and very big negative numbers in the exponent are very, very small numbers. And of course, even with all of this, overflow and underflow can happen, which means you might need to try to represent a number that's bigger than the largest number possible or smaller than the smallest number possible. So that's always a problem with computers. And that of course causes a lot of problems if you've done any programming. Underflow and overflow are pretty big issues with programming and dealing with all of that stuff. But in addition to all of this other stuff, there's another issue that is involved with this. And this is the part that might break your brain just a little bit. So what there's called is a bias number. And a bias number has to do with the fact of those positive and negative signs. So essentially, adding a positive or negative sign in a binary thing means that you're sacrificing a digit. So if you only have an 8-bit number and you have to have a signed integer, right? So that means a positive or negative, you're giving up one of those 8 bits, which means you've now moved from 256 values to 128 values with a sign. And that's a huge sacrifice. So in order to deal with that, IEEE and later on Google and other people have set up standards that have what's called biases in them. And essentially what that means is that you shift everything up. So if you've got an 8-bit exponent, you can actually then go from 0 to 255, right? So that gives you the whole thing. But you divide that number in half. So at 127, that's your breaking point. So everything over 127 is a positive exponent, and everything under 127 is a negative exponent, and 127 is a 0 exponent, which means it's just 1. So you're just multiplying by 1. That gives you back the full 8 bits of range because you're getting rid of that positive negative sign. So you don't have to deal with that anymore, but you know that you can subtract things so you can make positive and negative exponents out of a single positive number. And that's really, really cool. And by the way, a number like that is called an unsigned integer. It doesn't have a negative or positive sign. So you're not sacrificing a bit to do a positive or negative sign. So in the 1980s, IEEE set up a standard for precise half precision floats using 16 bits. And more lately, Google has actually done this as well for their neural network training. So what Tesla's doing here is not completely new. There's been other bodies that have done this before, but Tesla does have a real twist on things, and it has to do with the bias. So we're going to get there in just a minute. So again, just to give us some perspective, the IEEE standard uses 1 plus 10 for the mantissa. What that means is you get one number at the beginning before the decimal point, and then 10 digits afterwards. So your precision is actually 11 digits, and then you have 5 exponent bits. So if you add that all up, of course, 1 plus 10 plus 5 is 16, so you have 16 bits. So again, you've got 11 digits of precision, and then you also have an exponent that can go from 0 to 31 because that's 2 to the 5th power. And then of course what they do is they set the bias halfway between that, so that's at 15. So anything over 15 is a positive value, anything under 15 is a negative value in the exponent, and 15 is a 0 value in the exponent. Google Brain Float, which is a new standard, actually interestingly enough reduces the precision in the number to gain in range. So they have 1.7. So there's only 8 numbers in the mantissa as opposed to 11, so you're giving up 3 digits of precision, but you get 8 exponent bits for a full 16 bits again. So the exponent can now go from 0 to 255 as opposed to from 0 to 31. And again, the bias here is set at 127, so any number that's bigger than 127 in the exponent is a positive exponent. Any number that's smaller than 127 is a negative exponent, and 127 is an exponent of 0. But the range is actually a little bit worse than this because they're reduced by having 2 values for not a number and infinity represented in the scope of these standards. And also, just to be clear here, the bias number is stored as a separate number, right? There's just one location that stores this bias number. So, it just might be the number 127 in the case of Google Brain Float. So basically, since it only has to be stored once, it takes up almost no room, and that's the advantage of it. All right, so now finally let's get to Tesla. What is their new number format? It's called the configurable float or CFloat format. So there are actually 4 number formats that are within the boundaries of this configurable float format. So there's 2 8-bit CFloats and 2 16-bit CFloats. I'm mostly going to focus on the 8-bit CFloats because they're the most interesting part of this, but there's also a signed and an unsigned 16-bit CFloat as well. So the 2 8-bit CFloats are CFloat 143 and CFloat 152. And the numbers actually tell you exactly what's going on here. So the CFloat 143, for example, has a mantissa of 1 plus 3 plus 4 exponent bits. So again, that's a 1 number in front of the decimal point and then 3 digits afterwards, and then the exponent is 4 bits long. So again, here you can only represent 3 significant digits. So again, in base 10, again using base 10 as an example, the 42069 would be represented as 4.2069 times 10 to the 4th, but it can only be 4.207 times 10 to the 4th in CFloat 143. So again, here you have to round, and I'll talk more about this later because it actually is important how you round with CFloat. So obviously you give up a lot of precision here, but you're only dealing with an 8-bit number as opposed to a 16 or 32 or 64-bit number, which is fantastic for memory and for bandwidth. And as noted during AI Day, and I have a video on this, this is going to help Dojo be the fastest neural network training computer in the world. And this is in fact foundational to their effort to make Dojo the fastest neural network training computer in the world. But given how reduced this number is, how do you get the precision and range needed for calculations? Well, basically you use heuristics. You observe that we only really care about the weights, gradients, and activations when doing neural network training. And I think it's worth quoting the white paper here at some length. Quote, "One key property enabling this configurability is the fact that different parameters, namely weights, gradients, and activations, have different precision and dynamic range requirements to achieve high training accuracy and convergence. The configurability enables different allocations of the number of exponent and mantissa bits depending on the parameter being represented. Moreover, the numeric range these parameters span is also very different. Weights and gradients typically have much smaller numerical values compared to activations. The latter property allows meeting the dynamic range requirements of the various parameters using a configurable bias instead of increasing the number of exponent bits. The range of exponent values follows the principle of locality of space and time during the execution of a training network and do not change frequently. Thus, only a small number of such exponent biases are used in any given execution step, and the appropriate bias values can be learnt during the training." So it's all obvious now, right? You all understand exactly what we're talking about. Okay, there's a bit to unpack here, but I've given you the basics so you can kind of understand what's going on here. But essentially what they're saying here is they're using heuristics where they've noted that weights and gradients tend to be small, often extremely small numbers, while activations can be larger numbers. And the heuristics show us that we don't need massive precision in the numbers, so the mantissa can actually be smaller. We can sacrifice the mantissa for the exponent. And that's because we do need massive range, however, and the range needs to skew actually towards the very, very small, as weights and gradients in particular can become very, very small during training. So rather than a fixed bias value of like 127, the bias in the configurable float, or maybe it should just be called variable float, is simply a 6-bit unsigned integer. And this again, remember, is stored separately from the actual numbers, but you only have to store this once per matrix or whatnot, so you don't have to store very many of these. And that's actually what they mean when they say they only need to store a small number of exponent biases, right? If you had to store one for every single number, it wouldn't help at all because you'd be doubling the size of everything almost. But if you only have to store a few of these, then it doesn't take up hardly any extra memory and you get a huge advantage. And the advantage is that you get a number between 0 and 63 for your sort of bias exponent value. And it's constructed, and all the details are in the white paper. I'm going to kind of gloss over this because it's pretty complicated. But basically, it's constructed as giving you a max value of 2 to the 15th when the bias is set to 0, so up to 32,768. But as the bias value grows, the exponent actually gets smaller and smaller, all the way down to 2 to the negative 62, which is 2.16 times 10 to the negative 19th, or a really, really small number. So with just an 8-bit float, we have a range of 2 times 10 to the negative 19th, all the way up to 32,768, and that is huge. As opposed to even the IEEE 16-bit format, this gives you a massive, massive range. It's a bigger range than numbers that have twice the bit depth, and that's pretty incredible. So that's the genius of this particular format. But also note how this is massively skewed towards small numbers, right? We can only go up to like 32,000, but we can go all the way down to 10 to the -19th. And we need this range, especially the small range, to track tiny, tiny gradients and possibly weights as training goes on. Again, this gives us very low precision, only 3 bits of precision, but that's okay. We don't need that precision for quality training, as it turns out. Range is much more important. And as if this wasn't enough, here's an extra geek note. The range can be extended even more by using what's called denormal or subnormal numbers. There's no 1 required to start the mantissa, so you can have a 0 there as well. And this grants an extra order of magnitude, smaller numbers, in base 2 of course, as there can be a 0 at the front of the mantissa. If you didn't understand that, don't worry about it, but it's just a cool thing that they even extended the range even further. The CFloat 152, as opposed to the 143 format, reduces the precision even more, down to 3 digits total, to gain more range. And in this case, they can go from 10 to the -62 all the way up to 10 to the 31, which is a value of about 2 billion, as opposed to in the 143, the max value was 32,768. So this of course allows much bigger numbers than the 143 for activation values if you need it. And as I mentioned before, there's both a signed and an unsigned half precision format, which is a 16-bit format, included in this specification as well. And again, you can see the paper if you're interested in that. As an interesting note, infinity and not a number, which again is divide by 0, are not supported in this format. What they do is they clamp to the max and min values respectively. And again, they do this to gain extra range because you don't have to reserve bits and numbers for these particular values. And as with any good standard, you can perform math functions with larger number formats. So these numbers can be converted to float 32 or float 16, for example, and they can be multiplied with these larger number formats as well. And then of course they can be down converted back again to the CFloat format for storage. But that brings us to our last point. As the number is down converted back to CFloat, you have to round it. So again, with our example, 4.2069 times 10 to the 4th goes to 4.20 something times 10 to the 4th. So what is that something? Well, of course you have to round it. The traditional way to do that would be to round 69 up to 70 because that's the nearest number. But this format also supports what's called stochastic rounding. So it could be either 6 or 7 in this case. In binary, of course, it's a 1 or a 0, so it's basically a flip of a coin. But in the base 10 example, it could be either a 6 or a 7. So why is stochastic rounding important? Well, it allows for more randomness in the least significant digit, which A, helps with stochastic gradient descent, or determining where to adjust weights as you are training, and B, it actually helps to add some random noise to the training, which helps make the neural network model more robust. And the format also specifies this is a pseudo-random number, so it's repeatable if you use the same seed number. So that, in very long-winded fashion, is the basics of all of this stuff that's in the white paper. So if your head's not spinning too much yet, you might be saying again, well, why is this so important? Well, it's important because of memory and bandwidth. With billions of miles of driving data and massive neural network models, storage of all the numbers is one of the biggest issues facing Tesla or other big data and machine learning centers. And remember, this is now a proposed standard as well, so anybody can use it. And remember, of course, Karpathy talked about petabytes worth of data that they're storing for all of this driving stuff. So, we're talking about really big memory crunches here. But in addition to storage, it also reduces the memory bandwidth when moving all of this data around to do the matrix multiplication that's the basis of all of the training that's going on. Now, of course, there is a caveat. There is a conversion that needs to happen during a lot of the calculations. When you're doing matrix multiplication, you often need more precision, I assume at least, so some overhead is involved in converting these up to like float 32s and stuff while they're doing the actual multiplications. But this might not be too huge, as the format is specifically designed to multiply directly with different precision numbers. Anyway, overall, one of the big reasons Tesla's current supercomputer, and especially Dojo, which I'm sure is going to be designed specifically for this number format, are the fastest machine learning training supercomputers on the planet, is because of this number format. Rather than brute force everything, Tesla went back to the literal basics. How are numbers themselves stored and represented? What do we need out of a minimum size number? And how can we make storage and passing data as efficient as possible? And they came up with a whole new number format. If you don't realize it yet, I'm telling you this now. Literally anything and everything is considered by Tesla when they design their hardware and software. Wow. All right, I hope you found this episode fun and informative. It was kind of mind-blowing for me to work on it, so I hope you appreciate it. I tried to make it as simple as possible, but it's a little bit of a complex thing. Anyway, I hope you enjoyed it. If you did, please do hit the like button so other people can find this video, and of course, consider subscribing for more of this. As always, a huge shout out to my patrons on Patreon. Thank you all so much. I really appreciate all of your help. And of course, if you're interested in joining the club, check out the link in the description. And if you're interested in some awesome merch, check out the link in the description. We've got the Tesla t-shirt, which is super popular these days. Don't mess with Tesla. Lots of other t-shirts, tumblers, mugs, etc. So check out the link in the description and help the channel out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how clicking on a link and going shopping for a solar roof, a Powerwall, or anything on Amazon helps out the channel. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.